good. Okay, so the next speaker is Valentin Bickel.
That's good.
Okay, anything? Lunar South Pole boulders and boulder tracks, implications for crew and rover traverses.
Thank you very much. Where's my clicker? One. Thank you. So during the last couple of days, we heard many reasons why we're interested in going to Lunar South Pole. One of them being the presence of PSRs we would like to explore. We also heard from speakers like David Kring and others that Lunar South Pole is potentially challenging in terms of terrain. So the fundamental question that we ask ourselves at the moment is, how trafficable is the Lunar South Pole? And one specific question would be, what are the geomechanical properties of the South Polar regolith? Another question could be, can you derive these properties locally, so at the South Pole, instead of using values that have been derived at equatorial sites, such as the Apollo sites or Survey or Lunar Cod sites? You can imagine that it would be nice to confirm that these values that have been derived in situ during the Apollo missions, for example, are also valid for the South Pole before we go there. A more specific question could be, can we explore this on the South Pole with a crew or mobile assets, for example, the LER, Lunar Electric Rover? As David Kring mentioned on Tuesday, having a mobile asset on the surface would drastically increase the science output of a mission as crew is more mobile to move around. So what we like to achieve is high mobility, as you see on the left. What we like to avoid is getting stuck in soft soil, as you see on the right, happened to Spirit rover on Mars. And in fact, on the moon, one of the Lunar Cod rovers, which had a nominal sinkage of about 2 centimeters, sank down to 20 centimeters locally. And the LRV, Apollo 15 LRV, actually got stuck in a layer of soft soil and had to be retrieved by the astronauts manually. And these kinds of incidents highlight the fact that we have to be smart about trafficability at the South Pole. The tool that we use to better estimate these properties at the South Pole are Rockfalls. You see an example here. A rockfall is a boulder that rolled, slid, or jumped down a slope, covering a track. You can see that track quite clearly here. You can imagine that a soft soil would result in a deeper and wider track, whereas a stiff soil would result in a more narrow, less steep track. The thing is, before we can actually analyze these tracks, we have to find these rockfalls in satellite imagery. So usually it takes about 30 minutes for a human to go through one single image to find rockfalls, which is quite painful as we have to scan through thousands or hundreds of images. So what we did, we applied some previous work from last year where we use a convolutional neural network to automatically detect and map rockfalls in NAC imagery. And we did this, applied it to images from the South Pole, more than 2,000 images, summing up to more than 200 billion pixels in total. And all of this took only a single day to perform, which is quite fast. And this is possible because the network only needs about 5 to 10 seconds per image, compared to the 30 minutes that an experienced human operator would need. And by doing so, we found 79 rockfalls at Lunar South Pole, from the pole up to 85 south. And 58 of them actually right on the rim of Shackleton Crater or at Mons Malapert here. The red dots indicate these locations where we found rockfalls at the South Pole. This tool is going to be available on the awesome Moontrack platform very soon. So if you're interested in applying these tools, this kind of tool for your own research, you will be free to do so in a couple of maybe weeks, hopefully not more than months. All right, the first step of the analysis is then to compare the track appearances across the different regions. So we took our South Polar boulder tracks on the left bottom, lower bottom side of the slide and compared them to tracks that we previously found in previous work in pyroclastic deposits, Mare and Highland regions, you see in the middle of the slide, and also to PSR tracks that we found located on the bottom right of the screen. And what we find is that these tracks appear to be very similar across the regions, which indicates that the geomechanical properties across these regions might also be quite similar. The second step has then been to quantify our observations using the concept of, or the theory of static bearing capacity. So we applied equations from Terzaghi and Hansen to do so. You can imagine a block that sits on the surface of the moon with a certain weight, and then this weight acts on a certain area of the soil. So you have a force over an area which gives you a pressure. This is called the bearing pressure of that object. And if you imagine that this a soil holds that boulder and counteracts the downward pressure, you could call this the bearing capacity of the soil. And bearing capacity is interesting because we can use it to estimate the sinkage of landers, rovers, or crew. We can also use it to estimate the behavior of foundations. So if you're interested to place a heavy telescope on the surface of the moon, you might want to consider bearing capacity, for example. Another parameter that we look at is the rolling resistance of the regolith, where we use equations customized from David Carrier's work. You see on the right side a plot of a cross-section of a sphere or a boulder, a round boulder on the surface, where a boulder is driven down slope by its weight and the slope angle. And as we observe that there are boulders on the surface which stop rolling on inclined slopes, we can infer that there is a force that holds these boulders back, which is the rolling resistance. And knowing about this force can help us to better estimate rover energy consumption, and can also help us to better understand how rovers are able to climb slopes in general. All right, some of our results are shown here. Specifically, the bearing capacity as function of depth at the lunar south pole. The x-axis shows bearing capacity in kilonewton per square meter, and the y-axis shows the depth from the surface down to 5 meters. And the line that you see is a general bearing capacity envelope that has been derived for highland, mare, and pyroclastic regions in previous work, and that has been validated using in situ Apollo and lunar code data. And these little triangles in the upper part of the plot indicate our south polar boulder tracks, and you can see that most of these triangles fall either on the envelope or on the right side of the envelope, indicating that the capacity values are equal or higher in these regions, which is a good sign for us. What we also observe is at the bottom left, our coefficient of rolling resistance is about 0.05, which vaguely corresponds to the resistance that a standard-sized wheel encounters on large cobbles. All right, what we can also do is we can apply our values, our measurements to as a function of slope angle. You see on the x-axis now is the slope angle, on the y-axis is the bearing capacity again. And you see that if you go on steeper slopes, you have a lower bearing capacity, and quite drastic decrease of bearing capacity. And this enables you to plot bearing capacity as a function of topography. Here's the lunar south pole, where white colors indicate higher bearing capacity values and blue colors indicate lower bearing capacity values. The black spots are PSR regions. And you can imagine that this kind of map product might be useful for mission planners or engineers to understand whether their rover, where we know the weight and the contact area with the ground, might be able to manage a certain traverse, or if there might be some sinking-related issues along the way. You can also imagine that this map would be useful to understand if there are potentially scientific targets in the region that might be easier to access than others based on the bearing capacity. So one could, for example, combine this particular map with a slope map or other hazard maps to get a better feeling for future exploration in general. All right, with this I would like to summarize that talk. So we used a neural network to detect 79 rockfalls in the South Polar region. We then compared the track appearances across all these regions and found that they look very similar, suggesting that the mechanical properties are also very similar across these regions, which is a good sign. And we then quantified our results, our measurements, and found that these numbers actually support that initial finding. So we should assume that landers, rovers, and crew would not encounter any sinkage-related issues at the lunar South Pole, for example, at the rim of Shackleton crater. So it's also a good sign. And then we summarized all these insights into a number of map products. One of them have been showed here. And I hope that this kind of product might help to support the ongoing planning for future missions and in general. However, there's one thing that I would like to note, based on the incidents that I described before. We have still some knowledge gaps about lunar soil mechanics, and this might be a good point in time to think about how the Artemis or CLIPS missions might help us to advance our knowledge in lunar storm mechanics, and how we could use that advanced knowledge to minimize the risk of future missions on the lunar ground surface. And if you're interested in some of the resources that I showed, feel free to scan those QR codes if you can do so. And those will directly point you to the respective resources. Thank you very much.
Any questions?
Do you think that this track data indicating the similarity with other regions also may suggest that the water density may not be as high, or that the constituency of water in the regolith is not affecting at all the surface properties?
Are you referring to PSRs or in general?
Well, in general, near the pole, because it's postulated, Paul Spudis talked about,
Yes.
you know, much higher elevated water, even in the non-PSR regions.
That's a very interesting thought. What we can do at the moment is we can observe these tracks and we can only see that they are similar. So this is something which would be interesting to investigate in situ once we are on the surface.
I mean, it looked like the strength was even higher than you would expect. Is that not right? For the yeah, you're off to the right of the line.
Yes.
And you know, might that not be the effect of water, you know, or ice within the pores and things like this? That would, you know, make it a frozen ground instead.
Yeah, that's
of,
in sunlight. So those are values taken in sunlight
with
conditions.
a very high angle of sunlight. I don't know the average temperature or the effects, you know. Yeah,
So I would not expect
very low angle of sunlight. Yeah.
a high influence of water on that.
I don't know who it goes to.
So one more, which I'll take. So you were talking about experiments that you would fly on clips, soil mechanics experiments. Do you want to, you can have 30 seconds to say what you mean.
I think there are a number of things one could do. The easiest thing would probably be to document any interaction of a lander or a human with the ground, taking pictures, videos, and so on. For example, if you have a rover that drives a certain traverse, you could always have a camera pointing backwards, take a picture of the track to get a line measurement along the traverse. That would be very interesting to see. One could also deploy a penetrometer, as Lunar did, which is also very useful data. Those are probably very cheap and very simple options that could just be added to a CLIPS mission or a manned mission to the moon.
Okay, thank you.
Thank you.